In this video, I'll show how we obtain, how we solve the integral of a Gaussian function. So a Gaussian function or a bell curve is a function like this. Why also known as a bell curve? Because at x0, this function is maximum. Okay, in this case, it's 1. As we move to positive x or to negative x, since that is x squared, they both decay. So it has this shape that looks like a bell curve. Well, the integral of that function, let me make this a little better, no? So the integral of that function from minus infinity to infinity, the solution is square root of pi over alpha. Oops, a. Pi over a. So a is what we have here in front of that x squared. And this is what we want to show in this video, where the solution comes from. Okay, so it's a trick to show that. And what is the trick? Well, I'm going to multiply this integral by itself. Okay, nothing prevents me from doing the following. The integral in x, I'm going to multiply by the same integral, now with a different variable y. Well, the solution of this integral is of course the same. So the solution of this integral is of course the same. So to connect with what I had above, I'm going to say that this is the square root. Okay, well, what is the advantage of doing this? Well, I can write this as follows. It's a square root. I cannot forget that there is a square root in this story. But now I have two integrals in x and y written like this. X squared plus y squared dx dy. Why this is very nice, a nice trick, because now I'm going to do a change in variables. I'm going to use polar coordinates. And so instead of x, I'm going to deal with r and cosine of theta. So instead of x and y, we'll be dealing with r and theta. Okay. So this is going to be our changing variables. When we do that, we have to be careful. Now we also have to compute the Jacobian, which is dx dr, then dx d theta, and we have to compute this determinant of this derivative. So let me write it. So we have to get this determinant will be the Jacobian. So this is something that you learn in calculus. So here we have cosine of theta. Derivative in theta gives us minus r sine of theta. Here we have sine of theta, and here we have r cosine of theta. So need to get this determinant. This product gives us r cosine square. This product minus, with that minus plus r sine square. So it looked like a complicated thing, but you see, at the end, it's just r. So we change that variables. Now, so instead of dx dy, we are going to have the Jacobian r and integral in dr d theta. Okay, r, the limits for r goes from 0 to infinity. The limits for theta, theta is an angle, is from 0 to 2 pi. So let me rewrite what we had there. We have two integrals, one in theta from 0 to 2 pi. We have an integral in r and goes from 0 to infinity. So we have that r, dr, and now we have that exponential of minus big A x squared plus y squared is just r squared, no? Cosine squared plus sine squared is 1. So here we just have r squared. No? So, and don't forget, we have this whole square root. Okay. Okay, so this is now, what we have to solve. So let's continue with this. The first integral is very simple. It's just 2 pi. So I'm going to put this 2 pi, get some more space. Let me put this 2 pi here. Now, what are we going to do with that other integral? We are going to do a change in variables. Okay, so instead of r squared, I'm going to call it u, which means 2r dr is du. Correct. So that integral there becomes an integral in u, also from 0 to infinity. Now, this r dr becomes du over 2. Don't forget this 2 here. And then inside, we have this exponential of minus a u instead of r squared. And don't forget that we have the square root. Okay, now we continue. The 2 pi is still there. Now it divides by 2. What survives is just pi. And we have that integral minus a u du from 0 to infinity square root. All right, so you see that we are almost done, because what is this, the solution of this integral is going to be the exponential minus a u divided by minus a, with from 0 to infinity. So what we have is pi. Now, at infinity, exponential minus infinity is 0. So exponential of 0, this other extreme, is 1. Okay, so then what we get, the only thing that survives is that minus 1 with this minus gives us plus. And don't forget, we had the square root. There you are. We got our solution. So that's how we solve with polar coordinates.